right, morning everyone.
Good morning.
So just as a reminder, today is like, I guess our last official class meeting. Thursday, I will be here in this classroom and you're welcome to come and just work on projects. And if you have specific questions, you need specific help, great, I'll help. If you just want to work on stuff like with other people around because that's motivating, great, just come. How many people are planning to come and would eat a donut? Okay, wow, all right. So I just want to make sure I get enough donuts. So, all right, cool. I'll get a bunch. I will see you then. So today, I want to finish up talking about how to do memory allocation, which is like the last part of the operating system that we haven't talked about. If you're doing project 12B, then you'll need to do something with that. And then I want to talk about how randomness works, which is interesting. So, all right. So this is like, the book talks about this a little bit, but there's kind of a bunch that it leaves out. And I want to make sure. Right, okay. Yeah, and like everything, it's kind of like, there's two different places that it talks about it, so you just kind of have to look at both. So, memory allocation. Right, so we have these two functions, memory dot alloc, you give it a size, and memory dot dalloc, and you give it an address. And you'd better call dalloc with an address that alloc previously gave to you, otherwise who knows what the heck is going to happen. Obviously, like real operating systems can deal with this. If you give dalloc the wrong thing, it won't just corrupt the memory of the operating system. But we are not building a real operating system, so. So right, again, somehow it needs to keep track, the operating system needs to keep track of memory that's free. And so there's the memory, there's 0 to 15 is registers, and then 16 to 255 is static. This is the standard way that we're using memory in our virtual machine, right? 256 up to 2047 is the stack. And then 2048 through, I believe it is 2048. Yeah. Well, it doesn't say in this part, it says in the other one. Oh no, it does, 2048. And how big is it? I think it is, I don't remember. Here it is. No, it doesn't say. All right. Two questions. Does anyone happen to know how big the heap is? That would be a random piece of trivia. I would not expect anyone to remember that, but it's important because you have to know how much free space you have at the beginning. We'll figure it out.
It's probably when the screen starts.
It's probably on what?
Up to the screen.
Up until the screen? It could be. Yeah, is there anything else that goes, oh, yeah, maybe not.
Stack, heap, then keyboard and screen. Screen is the last, right? Or no, keyboard's the last.
Keyboard is last, yeah,
Okay.
I think. Yeah. So the screen starts at, so this is 2 to the 11th. The screen starts at 2 to the 14th. So yeah, up to 2 to the 14th minus 1, I believe. That sounds right, actually. I was looking at the code that I wrote for this when I did the project earlier, and I remember seeing the numbers 11 and 14 in there, so probably that's what it was doing. So, you know, the heap is this area of size, you know, 2 to the 14 minus 2 to the 11, which is available for programs to allocate arrays and objects. And the operating system kind of needs to keep track of this space and, you know, what areas in there are free and what are not, okay? So let's start by talking about a really stupid way to implement these. And unlike the you know, when we talked about like, oh, here's a stupid way to do multiplication, but you can do it for your project and it'll work fine. I'm not even sure that this actually works fine, but it's helpful to like start with something really stupid and then think about how we can do it better. So number one, stupid way. Okay, we start with, we just keep track of an address, which we'll call free, and it's initialized to, you know, 2 to the 11th. That is, it starts, you know, just pointing at the beginning of the heap. And when someone calls alloc, they want a certain size, you add size to free, and you return the old value of free. Okay, so in other words, like, you know, here's free, right? And then someone asks for a you know, some memory of this size, so you just say, fine, you can have this chunk here. I'm going to move free over here. So now, you know, free is now pointing to the next place after whatever they asked for, and you return them, you know, whatever the old value of free was. That's the address of, you know, where their block of memory is that they can use. Okay, so that's pretty simple, right? Just like every time someone asks for that size, you just get the next chunk, give it back to them, right? The problem is, well, what does dalloc do?
Frees up memory for later on.
Do nothing. Because the thing is, like dalloc, there's no guarantee that dalloc is going to be called in the same order that the allocs were called. So when someone says, yeah, I'm done using this memory, you're like, okay, that's nice, but like if all you're doing is keeping track of this free, that's like everything past this point is free and everything before it is used, like you can't, there's nothing you can do, because, you know, because maybe you've allocated, you know, this chunk is being used, and, you know, this chunk is being used, and this chunk is being used. Right, and everything after here is free. Oops. Right, and then someone comes along and calls dalloc on this. What are you supposed to do? Like, you just having this free is not enough, because like now I've got this chunk is used, this chunk is used, this is not, and this is not. And there's no way I can represent that just using free. So anyway, this works fine as long as nobody wants too much memory. Because like every time that someone requests memory, that memory is used and it's forever unavailable for anyone else. And you know, once you run out, you run out. Okay, so this is obviously really terrible. But you know, if you only use programs that don't need very much memory, maybe it's okay. I'm quite sure that well, I'm pretty sure, actually I don't even know, I don't know. my guess is that some of the test programs will not work if you do it this way, right? I'm trying to think like, Pong is a big game, but actually I'm not even sure, I don't know, I'm not sure that Pong is doing a lot of allocating and deallocating objects repeatedly. Like it allocates some objects at the beginning, like the object for the paddle, an object for the ball, some arrays and stuff. But I'm not sure that it's like generating objects and then deallocating them. Right, but if you imagine what some of you did for your Project 9, like if you made a snake game and every time that little food is generated somewhere, it's like you create a new object to represent the food. I mean, I don't know how you did it, but right, if you did that, then the longer you play the game, the more and more memory it allocates, and eventually you're going to run out. So, not a good way to do it. So, what do we do instead? We need a way to keep track of, and I think thinking about this is maybe key. What if, key to thinking about a good solution. So when we went and deallocated this, right, this section is now free, and this section is free. How can we keep track of the fact that there's these multiple segments that are free? Well, what if this segment, like maybe if we set free to point to here, but what if this segment then pointed to the next one, and so on, right? So we could actually make a linked list of sections that are free. So each one, we need to know how long it is, so we know like which part is actually free, and then we need to know where the next free thing is. And this turns out to work just fine. So we'll have a linked list of free segments. Okay, and when we start out, we just have one giant free segment that's the entire heap. But you'll see as we allocate things, we'll like split it up into smaller segments. So to initialize one giant free segment. Okay, but in general, it's going to look like this. So, and there's a picture that looks like this in your book. You can look at it if you want. So, we're going to maintain a variable called free list, which is a pointer to the the beginning of the list of free segments. And you can just make that a static variable in your. So this is like a static variable in the memory class. Each segment, well, we need to know how long it is. Okay, so that's going to be stored like right at the beginning. Like the very first memory location in the segment will store its length. Okay, and the next segment will store a pointer to the next, or the next memory location will store the address of the next free segment. Okay, so this is like next. And then everything after that is just, 1, 2, 3, 4, 5, 6, 7, 8. It's just, who knows what's in there, it doesn't matter, it's just available, right? And maybe this one is length 5. Maybe there's a really small one here, this one is length 3. 256. And then maybe this, like, since this is the last segment, perhaps, this just stores 0, null, right? There is no next one, so. Okay, and of course, I've drawn it like this. Conceptually, it's like we've got these segments, but of course, they're literally, like, this segment might be here in memory, and then there's a gap, and then there's another one here, and so on. So we just need to think about how do we, given this, how do we allocate some memory, and then how do we deallocate? So to alloc size. Okay, well, first of all, we need to go through and find a chunk of free memory that's big enough for the user's request, right? I mean, if there is a segment that is exactly the size that the user wanted, that's great, we can just use that. But in general, we just need to find one that's, bigger than the user's request, right? So there's enough space, because when the user requests, a certain size, we have to allocate a contiguous block of memory of that size. We can't give them several chunks that add up to the size they want. Doesn't work that way, right? So we need to find a free segment, that is big enough. We'll talk about what big enough means in a second. And there's a couple different ways we could do that. The book talks about two methods in particular. We could get a first fit. That means just, scan through and find the first. Right, you're just okay, I want something of size 5, so I'll go through here and I'll be like, oh, 8, that's big enough, so I'll use that one. That's the first one I found. You could also use something called best fit, where you find the smallest that is big enough. Right, so in this example, if I wanted something of size 5, maybe I would go look at here and say, okay, well that's big enough, so I'll remember that. If that ends up being the best one out, then I'll use that. But I keep going, I'm like, oh, this is better. This is closer to what this is actually exactly the size they wanted. So I guess if I find one that's exactly the size, maybe I would just stop. But maybe what if I wanted 4? Then I would say, all right, let's keep going. That's too small. That would work, but that's even bigger. So okay, in the end, I'll say, all right, this is the one I'm going to choose. Why would you do one or the other? I mean, so the first fit is probably going to be a little faster because the best fit has to scan through the entire list of free segments every time to find the best one. The first one might be a little faster, but in general, doing the best fit means you're not going to have as many pieces of random sizes left over. You'll tend to generate much smaller pieces that are left over. And it doesn't matter which of these you do. It doesn't matter. You can do either one. Zach.
With this method where we're storing the linked list variables in each free segment, what happens when we have a free segment? Say we get a request for a segment that's length 7 and we have a segment that's length 8, so we put it there.
Right.
We don't have enough space then to store the next address and the size in that free segment, so how do we
right.
use that again? Will it just be forever occupied?
Yeah, well, so you're absolutely right. And we have to think carefully of what we mean by big enough. Because yes, if yeah. Because yeah, you have to make sure that you've got enough space. You always need, every free segment has to be at least length 2. Right, because it has to store a size and the address of the next one. So you can't have a free segment that's only size 1. So if you had a segment of size 8 and you needed to generate a segment of size 7, you could do that, but basically you just need to throw away that one piece of memory that was left over and just say, I'm not going to use that. Here's what we're going to do. If the segment found, well, right, there's a couple of things here. So number one, when we allocate a segment, let's draw it like this. Let's say here we have 5. to say here. My point is that when we allocate, if someone asked for a segment of size 4, we could do this. We can basically say, all right, I had this segment of size 5, that'll work. I'm gonna leave this 5 here, and I'm gonna, like, this is the address I'm gonna give back to them. So like, you know, if I like called Alec, from my point of view, I get back this memory here that, you know, has, and there's 4 things available. What I don't know, and I don't need to know, is that actually, like, the address right before the one I was given, there's this thing that's keeping track of the size of this segment. And why do we need that? It's because when I eventually call dealloc, the operating system needs to know how big that thing was that just got deallocated, right? Because all it knows is, otherwise there's an address. And how does it know how long it is? Well, we're just going to make sure that that size is always stored in the address right before. So we'll return address to the code that called Alec and ensure the location before addr as the size of the segment. Okay, so yeah, like if someone asks for something of size 5, this one actually is not big enough because I can't give them 5 memory locations and also store the size, because I need at least one extra one to store the size. So right, there's a couple. So maybe I'll draw this over here. So scenario 1, if someone requests, let's say if someone requests size 4, right? Then I can, let me see if I can do this. Just let's see if I can copy. Oh, no. Right. So what I'm going to do is I'm basically going to take this segment here that I'm going to use to allocate the space. I'm just going to take it out of the list. So all I have to do is I need to, oops. I'm going to make this thing point to here, right? And I'm just going to take this, oops, all right, whatever. Okay, that's all I have to do. I just, the previous next pointer that was pointing to this segment, I just changed it to point to the next thing, right? So definitely get out your notes from data structures, because we are implementing our own data structure here. And then all I have to do is just return this address. The fact that this memory location actually is currently storing a pointer to this next thing doesn't matter, because I'm just saying you can use this memory. It doesn't matter what's there. Whoever asked to use it is just going to overwrite it with stuff, and that's fine, right? Scenario 2. Let's say that someone requested size, you know, let's say that someone requested size 5. We know that this isn't going to be big enough. So let's say we decide to carve out that segment from this segment. Okay. In that case, I can just kind of, I'm not going to have enough space here. I'll move all of this down. So what I'm going to do is, I'm basically going to kind of chop this segment so since they want size 5, I need 6, right? Because I need 1 for the length and then 5 for their request. And that would leave, and that is fine, because that would leave 2 here. So these two, like this memory, I don't have to touch, because this, well, I need to change this 8, right? It used to say 8, now it's going to say 2, because I just chopped that kind of in half, and I only have 2 left. And then down here, and then this will say 6, and then I return this. Right, so let me, can I draw a little scissors? Of course, I don't literally like cut anything. I'm just like, conceptually, I'm thinking as if I just like separated this little segment off of this segment. And you have to think carefully at like how much do you need there, because like they wanted 5. I need 1 extra to store the size of this segment, and then I need to make sure that at least 2 will be left over, because I need 2 for, you know, the segment that's left. So you need like their size plus 3. That's how big it needs to be. If it's the size plus 2, then basically you should just treat it like this scenario where you're going to have some left over, you just throw it away because not enough space. You know, and honestly, like this scenario is kind of an optimization. You don't really have to do that. So you could just say, I'm always going to look for a segment that's the size they want plus 3 or greater, and I'm just going to make their segment by chopping it off, and then like just leaving this segment here with a smaller size. That'll work fine, and you're welcome to do that. I personally did that version. It just seemed more fun to me, but this way, if you only do this scenario, you never have to mess with like changing pointers to point to the next thing and stuff like that. All you're doing is like chopping off a piece and returning that. Okay, and any ideas? What should dealloc do? If someone says, "Here, I'm done using this segment." You know, they give you this address, and you know that there's the size right before it. Zach?
Decrement the address and then find the end of the list, whether that's by like saving it in a variable or just traversing to the end of the list, and point it to that new free segment.
Okay. So you're saying we could take this thing, yeah, if we decrement the address, that's now, you know, the beginning of this segment. And I could just like put it on the end of the list. Yep, that'll work. There's actually no particular reason I can't put it on the beginning of the list, which is actually more efficient, because all I have to do is I make free list point to this thing that just got deallocated, and I just make this point to that, so we can, let's just draw that. Copy that. So if someone deallocates this, right, we're just going to, free list is now, we're not going to point it there, we're going to point it down to this thing, and then this thing, well here, like blue or something. And then we're just I'm gonna make this point to whatever free list used to point to. So we'll just add the deallocated segment to the start of the free list. All right, any questions about this? Any additional questions? This is all explained in your book. I think there's a few kind of details that the book leaves out that that I had to think carefully about, like about, you know, how much space you need and the fact that you can kind of have these two different scenarios you can do, but I think the book also suggests, you know, putting the deallocated segment on the end of the list. It's like, why? Why would you add to the end of a linked list? So, I don't know. So, you know, real operating systems do much more sophisticated things. They'll periodically do like defragmentation, like if it notices that there's a whole bunch of memory segments that are all free, they're all right next to each other, but they're all really small, it can like coalesce them into one big free segment, and that is helpful, right? Because then it's like, if you have a bunch of segments that are all size 5 and someone asks for something of size 10, it's just like, nope, sorry, I don't have one. But if it notices like, hey, actually all these, there's like 16 segments of length 5 all next to each other, oh, that's actually a big segment. You can even start like moving things around to, you know, you have to be careful, of course, because if you've given someone an address and said you can use this memory, and then you try to move it, well, if they're still holding an address to it, that's not going to work. However, many times there is actually an extra level of indirection. So when a program asks for like an address, it's like, oh, your memory is actually located here, so I'm going to like translate it for you and go look it up. And in that case, it actually worked fine. You can move stuff around as long as you keep track of, you know, where different programs' memories are. You can move things around and still have it make sense. All right. Cool. Well, that is that. So let's talk about randomness. Right, and of course, let me actually do this. Right, so if I, you know, in Python, I can say import random, and I can say random.rand int, you know, I got 85. Is that random? Right. 90. I mean, those are both pretty big, so I don't know. I'm not sure that's random. 6. Okay, good. I got a small one. But I just had been complaining that they were big, so maybe not right. Anyway, I mean, so 2 questions. Number 1, like, what does random even mean? Like, what exactly do we expect to happen here? You know, that would satisfy us. This is random. What do we mean by that? And then, of course, like, what actually happens in the computer when you do this. So any ideas, like, what would you say, you know, what is randomness? Any ideas? What do we even mean when we say, I want the computer to generate random numbers? Right?
Something that is sufficiently unpredictable.
Okay, so sufficiently unpredictable. I like how you use that word sufficiently. That's a good hedging word. But as we'll see, like, well, what counts as sufficiently depends a lot on our application. Yeah, Gary.
So, some
that will satisfy the user that seems unpredictable.
Something that seems unpredictable, right. Well, and that, I mean, I think that gets at like what is sufficiently.
Like user specific is not
Right. Right. Is there any other thoughts? Zach?
Randomness in nature, like true randomness, is kind of things that are things that, like, in order to predict them would require like so much knowledge that, like, we don't, it's not currently feasible to understand their outcome before we, like, actually just observe them.
So maybe like you're making, it's like not just whether it is predictable or not, but it's not feasible to predict or something. Yeah, I mean, you can actually get into a very interesting philosophical, or like somewhere at the boundary of philosophy and science, like, is true randomness, is it possible to have something that is like fundamentally unpredictable, or is it just that we don't, if we knew enough, that we could predict it, but we don't, right?
Electrons.
And yeah, I mean, I think people used to think, it used to be pretty accepted to say, well, no, like, fundamentally, if we knew enough information, then we could predict it. It's like computationally, we can't do it, or we can't actually learn all the information. Now that we know about like quantum effects and stuff like that, it's like, maybe that's not even true, because now, like, maybe it's not even possible to know. You know, it's like, well, I can know like the position of this particle, but then I don't know its velocity, and like, well, so I can't actually know everything about it. So maybe like predicting is not even possible. Anyway, okay, and I'll add one more thing that typically we talk about the randomness not of like a single number, but of a sequence of numbers. Because if you just have one number, then it's like, well, I mean, is 7 random? I mean, I don't know, like, it's just a number. It doesn't, numbers cannot be like random or not in and of themselves, right? It has to be like in a context where I'm generating a sequence of numbers, and the question is like, if you know all the numbers that have happened up until that point, can you predict what the next one is or not? Say randomness of a sequence of numbers. Right, so in other words, you could look at a sequence of numbers and say, you know, how random is this sequence, but you can't look at an individual number and say anything about how random it is. Yeah.
I think a better kind of like definition than what we've already come up with for randomness might be a sequence of numbers where you can't predict the next number based on the previous sequence.
Right, sure. So, sequence, where you can't predict the next based on previous. Right. Yep. Those are all good. And I mean, you know, it's actually surprisingly difficult to come up with a really good definition of randomness. It's kind of those things where like, well, I know it when I see it, but if you force me to define it, I'm just like, not really sure. All right, but this is all good for our purposes. So, what are some applications of randomness? Because the application, and specifically like having computers generate random numbers, the application you have in mind changes the requirements we have quite a bit. So ideas, what are some applications of where you would want a computer to generate random numbers? Okay.
I remember in game development, I was like making some game to where things would be falling from the top of the screen, and I needed it to be random to fall from like a different part
Yeah,
from the
okay.
top of the screen.
So I'll just say like games, but just like, what am I trying to say? Well, yeah, I'll just say games, but you're right, like that kind of the kind of thing where that you would talk about in a game as being like RNG, right? Where it's like there's something that's going to happen, and I want it to be unpredictable because that's more fun for the player if they don't know exactly what's going to happen. They have to like react to whatever is happening, right? For sure. Morgan?
Like online gambling sites.
Okay. Yep. Or say online gambling, right? Okay. What else?
Statistics.
Statistic. What do you mean statistics?
It's like creating a random sampling of a data set.
Oh, right. Okay. So like random sampling. Is there here?
Some people like to roll dice and things like that, flip a coin, get an answer for themselves randomly.
Okay. Yeah. So I mean that maybe has to do with like games or random sampling, but yeah, I mean like you could say simulate coins, dice, etc. Okay. What else? There's one really big one that no one said.
Encryption.
Yes,
Oh.
cryptography. Right, because like you might want to pick a random encryption key or something. If it's not random, then that means like, you know, it might be much easier for someone to guess. If it's like, you know, I pick my cat's birthday or something. We all know that like making up a random sequence of letters and numbers is a better password than like your cat's birthday, because there's no, if it's truly random, there's no information that anyone could use to figure out that it's more likely to be one thing than another. It's just like they would have to guess every possible password. Okay. Any others? One that I am fond of, so within games, I'll like, there's like at least two kind of sub things that I know of. So one is like, you know, random events, kind of like what Kate was talking about. You know, something's going to happen in the game and you want it to happen randomly. The other is procedural generation. I'll mention that a little bit more later. But for example, Minecraft, right? Minecraft is the big example where you know, the world that's generated is random in the sense that just looking at one part of the world, you don't necessarily know what, you know, if you go explore in a direction, you don't know what you're going to find. And we'll see that's actually fundamentally different than the other thing for some reasons. But all right. So some of these I would say are like need to be more unpredictable than others, or it's like important to us that they're like really, really unpredictable. So what do you think? Which of these is it like important that they would be as unpredictable as possible? Or that our randomness would be as unpredictable as possible? Right? Yeah, cryptography for sure. What else? There's one more in here that's very important. Yeah. Yes, online gambling, because if the random number, if the numbers you're picking, if there's any sense in which they're not completely unpredictable, then someone out there is going to figure out how to predict just enough that they're going to make a ton of money, and like you're going to lose a bunch of money. So it's really important. And obviously cryptography, right? I mean, I guess it depends on, you know, if you're sending messages to your friend, you know, and you're just like, hey, let's use this cool code, that's fine. But if you're like a government, or you're not a government and you don't want government to read your messages, whatever, that's important. Some of these other things, like, you know, for games, like, does it really, really matter if it's completely unpredictable? As long as it kind of seems unpredictable to the user, that's good enough, right? Because no one's going to sit there and be like, well, at least that's not true. I can certainly imagine scenarios where if a game is super competitive or something, that people would actually put in the effort to figure out how to predict events in the game. I'm sure that happens, but for the most part, it probably doesn't matter. If you're doing like sampling for, you know, scientific applications or simulations, probably doesn't matter as much either. Zach?
And also for things like online gambling, you might be able to use like actual truly random like sources of
Yeah.
of randomness, like atmospheric noise or
Yeah,
radioactive decay.
absolutely, that's, yeah.
But for cryptography, you need specifically pseudo-random number generation in a lot of
That's not
applications,
true.
right?
No, that's not true.
It's true.
No, I mean, it depends on what you're, if you're just like picking a key, so like, we're gonna pick a key that we're gonna use to communicate. If I can get an actual, like, real source of randomness to generate the key, that's great.
Oh.
There might be applications of pseudo-randomness, but anyway, but yeah, so that's the next thing we're gonna talk about, is like, where do you get random, where does randomness come from? So, sources of randomness. And there's really kind of two main ways that computers generate random numbers. So one is using some kind of hardware, or like, I would say environmental or physical sources. Okay, so typically this is like, in other words, we're using some kind of physical process that, as far as we know, is unpredictable, and then using that to generate random numbers. So using an unpredictable physical process. So for example, I mean, this is like super old, right? So like dice, right? Why do we use dice? Well, it's because when you throw a die, just like because of like, it's like a chaotic system, right? It's very, very hard to predict, because like the die could be like slightly different at the beginning and it'll end up in a totally different position at the end once it's bounced around the table a bunch. And people have known this for a long time, right? So, dice, coins, interstellar radio signals. So there is a website called random.org that maybe you've seen me use before. I often use it like if I need to generate a random order for students to go presentations or something like that. And the way that site started in 1997, and they were like, and actually they were developing an online gambling application at first, which is kind of their impetus for it. It's not really involved in that anymore, but they literally like, they got a radio and they like tuned it to something where no one was broadcasting. And these days I think they actually like have some kind of radio receiver that's like pointed at an area of the sky where there's like nothing that we know of. It's just like kind of random radio signals that are coming. And they like sample it and they throw away most of the bits and they only keep like the very low order bits or something like that. And as far as we know, it's pretty unpredictable like what radio signals are coming from like that place in the sky. So, lava lamps. So there's actually I have an article to show you, this is fun. So Cloudflare is like an internet company. I mean, they like run a bunch of, internet infrastructure and provide internet kind of services. So apparently in their office, they literally have like a wall with hundreds of lava lamps that they're taking pictures of every millisecond and then using that to generate random numbers because, how the lava lamps move is unpredictable. And so, there it is, there's people looking at the lava lamps. I mean, like, did they need to do that? No, not really, but it was just kind of fun. But apparently, like, it's not just for show. Like, they really do take pictures of it, like, once a millisecond, and use it to generate some random numbers that then go into, like, internet security somehow. I don't know. I mean, like, this article from Fast Company didn't, like, go into the actual technical details of what they do, but, yeah, fine.
Would it be more difficult to use lava lamps since they move really slowly?
You're saying like because
Like each photo would be almost identical to the one before, right?
right, but I think like I think they're probably, they're taking the photos and running it through some kind of hash algorithm or something that like even a small difference in the initial image could generate very different results. That's my guess. Again, it did not explain the technical details of what they actually do. So, I don't know. I just thought it was fun. So those are all like kind of really external things that you could try to use a computer, you could like measure somehow and then get those numbers into a computer. But they're gonna be fairly slow to generate data, right? Imagine if you need a bunch of random numbers and so you sit there like rolling a die and then putting them into your computer, that's gonna be slow. So there's actually, these days, you can get computers with actual hardware devices in them that generate random numbers using a physical process. So for example, so like I know some work using thermal noise. So for example, you can measure the temperature of your processor or the temperature of something in your computer, and only keep like the very lowest order bits of it or something, and that would, right, like the minute temperature fluctuations of this thing are kind of unpredictable. There's also things based on the photoelectric effect. There's like, I know I've seen things where you've got like, arrange some resistors in a particular way that like kind of the signals that's going through it is kind of chaotic because it kind of feeds back into itself in a weird way. Oops, sorry, the pen is running out. Anyway, so those things like, like the actual hardware devices in a computer for generating randomness based on some kind of thermal noise or something like that, like that is really intended for applications in cryptography, right? Because it's like, if I want to generate a random key to talk to a website, I can actually like issue a CPU instruction that will, cause it to go sample this specific device in my hardware, generate some random numbers that would be extremely hard to predict what's going to come out of that. And so I have a pretty high level of guarantee that like, it doesn't accidentally depend on some other values that I had in my program and they're going to be unrelated. And the fact that they're like actual built-in hardware devices means they can typically generate random bits pretty quickly, which you would want in some applications, depending on what you're doing. So there's like actual hardware, embedded hardware devices for generating randomness. Right, you might even, if you're interested, you should look up, because I know, depending on, like it's possible that your laptop has one of these in it. It's possible. Some newer processors actually have one of these like randomness generating devices built in, and you may happen to have one of them in your laptop. It's kind of interesting to see if you can figure out what kind of processor you have and look it up and see if it has some kind of randomness generation thing in it. Even if you do, I'm not sure exactly how you access it, but could be there. Okay, so obviously all this kind of stuff, right? This is like suitable for cryptography or online gambling, etc. Right? This is like the highest quality randomness is always going to come from some kind of physical source like this. Okay. However, there's another big class of things where we get randomness from, which is called pseudo-random numbers. Pseudo-random number generation. PRNG. Okay, and if you call random.random in Python or the random class in Java, this is what you're going to get. If you actually want a physical source of randomness, you'll have to do something special to access it. But kind of by default, you're going to get pseudo-random numbers. So what are pseudo-random? Why are they pseudo-random? Well, I'll say sometimes we want a sequence that looks unpredictable. But is actually deterministic and repeatable. Okay, so in other words, it looks unpredictable, but it actually, on some fundamental level, it's entirely predictable. If you kind of know the initial state, you can then like just use some mathematical function and generate all the things in the sequence, and it'll be exactly the same every time. Anyone think, like, why would you want that? Why would you want random looking numbers that actually aren't random in the sense that you can generate them according to some formula? Me looking back at some of our applications. Anyone think why you would want repeatable? Yeah, try.
Not really worth the effort.
Okay, well, so for sure. It's much easier, as we're going to see. And so if you don't really care about the extra randomness, then it's not worth the effort. And so you might as well do a simpler thing. For sure. Simon?
In a game or a simulation, if you're trying to debug something, it would be nice to know exactly what state.
Yeah,
it was in.
exactly, yeah. So that is an important thing. One thing that's not on this list is random testing, which is a thing you can say like, oh, this should be true for all possible inputs, and then it can like generate random inputs. And if you find one that doesn't work, you want to be able to repeat that. So you can, yeah, or right, if you're like, oh, I want to know, you know, exactly what happened here, so that I could like debug it. Yeah. Does someone else have their hand up? This is actually very important, like, for Minecraft, right? And if you play Minecraft, you're familiar with this. Like, if I say, oh, I found this really cool world, here's the seed, and I tell you like my seed, and you can put that seed in, and you get the exact same world that I had, right? Why is that? Well, it's because the randomness is actually entirely predictable. It's generated by a deterministic function from that seed. And so even though it appears random, which is why like the world doesn't just look completely regular or whatever, but yet it's actually generated by that function. So that means that, you know, we're always going to get the exact same. I mean, don't even worry about sharing. Like if you quit Minecraft and you start Minecraft again, the world looks the same as it did the last time because it's just generating it from this function. Yep. Cool. So how does this work? I mean, it doesn't even seem possible, right? It's like, how could you have something where it's just a function that's generating like things in the sequence? So you're saying it's predictable because you can just run a function to get the next thing, but it seems unpredictable? Like how could that be, right? And it's a big research area. It's not easy to design functions that work this way. And a lot of the things that people used to use, you know, people have realized, oh, but, you know, in certain ways it is kind of predictable. And again, depending like how much you care, that may or may not, that may be okay or may not be okay. And so there's a lot of trade-offs where you can, you know, if you want something that's really, really fast, but you don't care that it's like super random, or you want something that's like really high quality randomness and you're okay with it being a little slower, you know, there's trade-offs. So, one simple kind of pseudo-random number generator is called a linear congruential LCG. And it works like this. If I have a value xn, then the next value in the sequence, xn plus 1, is equal to a times xn. So you multiply the previous value by something, you add something, and then you mod by something. Okay, that's it. Obviously, if you leave off the mod m part, this looks extremely predictable because it's just like the points just make like a line. With the mod m, right, it's going to be jumping around inside this interval from 0 to m, and it may look less predictable. And obviously, it matters a lot what you pick for a, c, and m. And so, like, if you go to the Wikipedia page on linear congruential generators, you'll find a big table of different values of a, c, and m that have been used over the years in various applications. But you know, you try to find values of a, c, and m that give you good properties. So for example, I happen to know, as I looked it up, that the Java random class does in fact use an LCG with, so m is 2 to the 48. So picking m that's a power of 2 is nice in some ways because to do mod m, all you have to do is like chop off the last 48 bits. And you don't actually have to do any division. So that makes it a lot faster. However, it makes it slightly less random. So it's kind of a trade-off. Or it makes it so like certain bits of the output are going to like repeat with them. You know, there's just like different things that maybe are not quite as nice. A C is 11. And A is 5, D, E, E, C, E, 6, 6, D, base 16. Why that one? I have no idea. That's just what it uses. And like, you can go look at the source code, and it's like right there. You can see how it works. Python does not use an LCG. It uses something called a Mersenne twister. And I went and looked it up to try to see if I could explain how it works. And I was like, nope. I mean, I could, but it would take probably half an hour because it's just like, it's kind of complicated. And there's tons of these. I mean, there's tons of different kinds of PRNGs that give you different nice properties. You know, generally you're trying to design them to be as fast as possible, but give you good properties, to be, you know, nice and random. And different ones are used for different things. But so given all this, it's interesting thinking about how could we add randomness to the hack platform that we've developed. So of course, you could code up like a linear congruential generator. And I think 1 or 2 people actually did this on Project 9. It's not too hard to code this. The question is, where do you get kind of the initial value from? So that's called a seed. A seed would be like the initial like x0 that you pick. And if you just always pick your seed to be, say, 0, well then you're always going to get exactly the same sequence of random values every single time. And maybe you don't want that, right? Maybe you're like, well, I want it to be like initialized differently so that, you know, it really is unpredictable. Because imagine if like every time you start your computer and ask a random number, you always get 7 as the first one, and then you get 14, and then you get 12. That'd be kind of weird, right? Yes, it's nice that it can be repeatable when you want by like giving it a specific seed, but otherwise you're like, no, I wanted to just start with a random seed. Well, how do you pick a random seed in the first place if you're generating pseudo-random numbers? Well, you use one of those other methods of getting like something from the environment. But the thing is, you only have to do it once. Like when you start up, you get some random value from the environment somehow, and then you use that as your seed, and then from then on, you're just running this function. Many computers, so I know like, I don't actually know what Java and Python do. Often it works something like, you know, at the time that you want to initialize a generator, it looks at the clock, and it picks like the microseconds value of the clock, and it uses that or something like that, right? So it just uses like the current time, which again, if you're only looking at like microseconds or something, then it's pretty unpredictable exactly what microsecond you're gonna happen to call and get a seed at. No, but we couldn't do that in the hack platform because it doesn't have a clock. Maybe the next best thing, so something that might work is we could add a counter, and every single time that there's like a cycle, it could add one to the counter. So that's kind of like a clock. It's not like the actual time, it's just like how many cycles have gone through. And maybe you could use that, like when someone wants, so you could add a counter and then add like an instruction that would ask for a random value, or just would ask for like the current value of that counter, and it would tell you. And you could use that to initialize your linear congruential generator. I mean, it's not great, but like, that would actually work, and we could actually do that, you know, given what we have. I think many of you like that need to randomness, you use the user as a source of environmental randomness, right? It's like, oh, please enter a random number. But that's, I mean, again, if you don't need super high quality randomness, that's a perfectly valid way to do it. But any questions about any of that? All right, I think that's all I have to say. I will see you on Thursday if you want to come. Yeah.
I have a question. It's just about the VM emulator.
Sure.
So for the ones that have text,